Hello, welcome to a new virtual tour of the European Southern Observatory, or simply ESO is the acronym. My name is Farid Char, and with the producer Hector Salas, we are going to be your guides during this trip to the ESO Paranal Observatory. So just a little bit about me. I have more than 15 years of experience in astronomy outreach and education. I am one of the guides of the observatory since 2010. Um, well, and regarding my personal hobbies, I am interested in astrophotography. So ESO wants to be with you during these virtual visits and bring astronomy directly to your home or wherever you are. So as I told you, I am not alone. I am with producer Hector Salas. How are you, Hector?
Hi Farid, happy to be here once again. So my name is Hector Salas. I'm a PhD student at the Leibniz Institute for Astrophysics in Potsdam, Germany. I work mostly with topics related to the circumgalactic medium, that is the environment of surrounding galaxies. And I have been a member of the team of guys for Paranal Observatory since 2019. I started while I was doing my master's degree in the University of Antofagasta. And today I'll be the producer, and that means I'll be checking the videos, but also checking all your comments and questions. So please, if you have any doubts, send those, and we'll try to address it at some point during the tour.
Okay, thank you, Hector. So, so please remember you can send all your questions and comments during all this streaming, and maybe and later we are going to answer to all your questions or comments. Okay. So okay, now we are going to start immediately, and I want to help you to understand the place of our visit. So we will begin this journey with some information about the European Southern Observatory, or ESO. So ESO is composed of 16 member states. The headquarters of ESO are located in Germany. We are going to see a picture to understand this. So the headquarters are located in Germany, and also Australia has joined ESO as a strategic partner. Um, so Chile is the host state and is the home of all ESO observatories. So from the 1960s, and with those objectives in mind, ESO has chosen one of the best places on the planet for astronomical observations, the Atacama Desert in Chile. So during this period, Chile started several site explorations in order to attract international observatories, such as ESO, to our country. As a result, Chile offered its territory, and ESO did choose the more suitable areas. So the mission of ESO is to design, build, and operate astronomical observatories. And what for? Well, to enable important scientific discoveries and incentivize the promotion and cooperation in the astronomy field. Well, right now you will see a picture with the three observation sites of ESO in Chile. So in first place, we have the Chajnantor Plateau. This is the site of the ALMA radio telescope. ESO is part of this place for radio astronomy alongside other international partners. Additionally, south of the Atacama Desert at 2,400 meters, we have La Silla Observatory in the Coquimbo region in Chile. So this ESO observatory is the home of several telescopes such as the NTT or the 3.6 meter ESO telescope, and this one is using the HARPS instrument, and this is an exoplanet hunter. And finally, we have the place of our visit, Paranal Observatory. This ESO observatory is the home of the Very Large Telescope, or VLT. This is the most advanced visible light telescope on Earth. And in the next few years, we will also have the Extremely Large Telescope, or ELT, the biggest visible light telescope on Earth. Also, the CTA will be an array of telescopes focused on capturing the gamma rays. Okay, so now we have a better picture. So let's travel to the Paranal Observatory. Now, virtually, you will see some kind of flight over the Atacama Desert in the north of Chile, about 1,600 meters sorry, 1,600 kilometers north of the capital, Santiago, and specifically about 130 kilometers south of Antofagasta, the regional capital, and about 90 kilometers north of Taltal, the closest city. So now we will go toward the mountain top of Cerro Paranal. Do we have the video, Hector?
Yeah, I'm having a bit of technical problems putting the video.
It's okay. So, well, in a few moments we will see this video, but basically we are going to the mountain top of Cerro Paranal, and Paranal is located at 2,600 meters above sea level. Now, this mountain belongs to the coastal range, and despite its altitude, it is located at just 12 kilometers from the coast. So only 12 kilometers away from the coast. Now, where is the ocean? The Pacific Ocean is located below of a cloud cover. Okay. Okay. So now we are looking at the virtual flyover over the Atacama Desert. So you will see in a few moments we will arrive to the Paranal Observatory, and you will see this cloud cover I was talking about. And in this case, well, you will ask yourself, well, why those clouds? Because in the mountaintop, in the rest of the Atacama Desert, is so clear, dry, and lonely. Okay, well, the presence of the cloud cover in the horizon, as you will see in a few moments, is because of the influence of the Humboldt Stream. This is a cold stream near the coast of Chile and Peru, cooling the atmosphere and causing a phenomenon called thermal inversion at about 1,000 meters above sea level, keeping below the cold, humid, and basically bad air for astronomy about the layer. Instead, about the layer, we have the hot, dry, and less dense air. So this is the good air for astronomy. Okay, so the clouds are blocked by the coastal range, and near Paranal, the mountains are high enough, surpassing 2,000 meters above sea level. Now, what about other natural barriers around this area? Well, about 200 kilometers to the east, we have the Andes Mountains, and with very high mountains, more than 6,000 meters above sea level. So this is another natural barrier blocking the clouds from Argentina and Bolivia. So the main result is this landscape, a place with an average of more than 300 clear nights per year, with a very clear and transparent atmosphere, making it ideal for observing the night sky. Also, here we are far away from artificial light sources because of human activity. I mean light pollution. So this is one of the best places on Earth for astronomical observations. So right now we will change the view to have an even closer look to Paranal. So as you can see here, this is not an ordinary mountain. And now we can see the different telescopes and structures in the mountain. We are at the summit of Cerro Paranal. So the meaning of this word, Paranal, in the Quechua language, Paranal means whirlwind, possibly because of some whirlwinds forming in the desert. However, as I told you already, the atmosphere is extremely quiet in this place, so this observatory is a true oasis. And you will see how in one of the driest deserts we have a lot of life and a lot of science. Okay, so right now we will visit the summit of Cerro Paranal. So in front of us we have the very large telescope, or the VLT, its acronym. So if you see the amount of buildings, 4 giant domes and other 4 small and rounded ones, Well, it is clear that the Very Large Telescope is not only one, but a very special array of telescopes. So all this facility is the most advanced optical observatory on Earth. Okay, so let's take a closer look. So in first place, here we have the 4 unit telescopes or UTs, and each one has a primary mirror of 8.2 meters of diameter. Okay, so the big ones, the giant ones in your screens. And the other small ones, like this one, are the auxiliary telescopes or ATs, each one with a primary mirror of 1.8 meters of diameter. Okay, so we have the second one here, and we have this one, and we have the last one here. Now, coming back to the big ones, each UT, each big telescope has a name in Mapudungun language. This is the language of the Mapuche culture, natives from central and south of Chile. So here we have Antu, which means sun. This one is Cuyen, and this is moon. Melipal means 4 stars, but this is a reference to the Southern Cross constellation. And this one is Jepun, and this is a reference to the planet Venus. Okay, so these are the names of the big telescopes. Now, the closer ones, as I told you already, are the auxiliary telescopes. Now, those telescopes are very special because they are mobile and they can be moved using a rail system here up to 30 different positions because we have some kind of stations scattered in this platform. So they were specifically designed to work all together as a single big telescope with a variable diameter. So the small ones are able to reach up to 200 meters. We can simulate a telescope up to 200 meters, as you will see in a few moments in a short video. Okay, so in this animation, I want to talk about the technology, the specific technique. The technique to combine light from several telescopes is called interferometry. So we are able to observe much more specific details if you compare this with the individual telescopes. So thanks to interferometry, we can simulate a giant mirror to distinguish details up to 16 times fainter than a single telescope. So why don't we make small telescopes and combine them to create a huge telescope? Well, interferometry also has limits, and some information is lost during its travel. However, it is still an excellent solution to observe objects too difficult to observe with our current technology. Okay, so right now we will come back to the tour screen. So now you will have the chance to visit a telescope. We are going to visit the UT3 Melipal. We can't enter all the telescopes, but don't worry about that because the 4 ones are identical in size and shape. So the only difference are the instruments inside. Now you can know more information about the instruments if you visit the ESO website. Okay. So now we are going to access the UT3 telescope, and here we are. So what can you see? Well, this is a giant telescope. At this moment, we are on the last floor of the telescope, at the same height of the main mirror in front of us. So the mirror has 22 tons with 8.2 meters of diameter and only 17 centimeters thick. I am going to do a close-up to show you. So this mirror is it was created from a ceramic and flexible material. The name of this material is Cerodur, and the surface is a very thin layer of aluminium. So this is the reflective material of this mirror. And by the way, the mirror has a concave shape, so it's like a spoon. So if you consider that this mirror is so big and so heavy, okay, remember 22 tons, and you need to consider that during the night we have to, let's say, move the telescope and put the telescope in some different positions, looking at the sky. So just because of gravity or physics, the mirror can suffer some deformations in the concave shape. So how can we point the telescope to, well, to any place in the sky without breaking the mirror? Okay, I will show you the telescope from another angle in order to explain that. So I will show you the telescope from this floor, from this level. So I want to explain a little bit more about an important technology we are using here. So the mirror is basically mounted over this white structure. Okay, so this is a cell supporting all systems assisting the mirror, including something called active optics. So let's do a close up because I want to show you some little gray boxes over there. The gray boxes are called actuators. They are a kind of piston, and we have 150 in total. They are controlled by a computer. Now, they are acting on the mirror during the observations in order to keep the optimal shape of the concave mirror. Otherwise, it could suffer deformations just because of gravity. Now, those deformations, imperceptible in a first view, could be critical in the result of the observations. Okay, so now, once I explain this technology, I want to explain a little bit how the telescope is working. So in order to do that, I want to show you a quick animation so you can understand better this concept. So the first thing is, of course, to open the doors. And this is, of course, an exaggerated view. But the first thing is that the telescope will receive the light from the stars. So in this case, the light will reach first the primary mirror. The light will be concentrated, reflected to the secondary mirror, reflected again to a tertiary mirror, and from there the light will be reflected to one of the three possible instruments. We have three instruments, in this case represented by the blue, red, and green boxes in this animation. But essentially, we have three different possibilities, three different instruments in order to receive the light. So in this case, this is one of the instruments. Okay, this big machine here, and by the way, you can see some of the engineers working in this area. The other instrument is located in the other side, it's not visible from here. And the last instrument is located, in the base. Okay, so we have three possible instruments. And once the light is reaching the instrument, this light is converted into a digital signal, and this digital signal is transferred to the control building because the astronomers are working from another location. They are working from a control building. And that means that during the night, this telescope and all telescopes are completely in darkness, are completely empty at night. So no one is here at night. All the people is working from a separate location, and this will be our next stop. We are going to do a quick visit to the control room. So we are going to visit the workplace of the astronomers. But essentially, this is how the telescope is working at night, and we are doing a remote control of the telescope every night. Okay, so we are going to finish the explanation here. We are going to move outside because, as I told you already, the next stop will be the control building. The control building is located here. As you can see, this place is located in the mountain top, but not at the same level of the telescopes. Okay, I will show you another view of this control building. As you can see, it's a big facility. So in this location, we have the control room. I mean the workplace of the astronomers. But before going there, we have some moments to answer some questions from our virtual visitors. So, Hector?
We don't have any questions so far. We have some greetings from Sway Graven, who sent us love from Amsterdam. But no questions so far. So let me ask you one of the usual questions people do in the in-person tours. What kind of maintenance is necessary to do to the telescopes to keep them in perfect shape for the observations?
Sorry. Yeah, sure. This is a typical question from the visitors to Paranal. So let me go inside because, well, the most important maintenance in this case is for the mirrors. So, for example, Paranal was inaugurated at the end of the 90s. Okay, so the mirrors are all the original mirrors. So basically, the mirror has that they have more than 20 years. In order to keep the mirrors in optimal shape, we have to do two specific maintenance. One of them is something like an easy maintenance, and in order to do that, we have to rotate the mirror a little bit. And a couple of engineers usually will spread a carbon dioxide snow on the mirror. This is something like a foam. So this element will remove dust from the mirror because you need to remember we are in the Atacama Desert, so we have dust in the environment. So this is usually enough to keep the mirror, let's say, clean in general terms, and you need to do that about once a month. And this is more or less a simple maintenance, so you don't need a lot of people to do that. But the other maintenance is a little bit more complex, and in this case, you need to extract the entire mirror from this building. So in this case, you can see here the mirror, but you also have the white base. So you need to extract both things. You need to extract the mirror and the white base. And to do that, we need to use special, let's say, door here. So if I show you from the outside, you will see here that there is yellow structure. So this yellow structure will receive the mirror, okay, and we have a vehicle at the ground level. So this structure will, let's say, drop the mirror very gently, of course, to the vehicle, and we have to transfer the mirror to the base camp. We have to transfer the mirror to a special facility for a process that is called a recoating. So the recoating is essentially a process to remove the aluminum layer and to put a new one. Okay, we remove the old aluminum with chemicals and we put a new aluminum layer. So essentially, when the mirror is ready, after maybe 3 or 4 days, the mirror will look like a new mirror because you are actually changing the reflective surface. So after that, we have to return the mirror to this platform. We have to use this structure again. So we have to lift the mirror and we have to reinstall the mirror in the telescope, and the telescope will be ready again for observations. So that's it. That's how we are doing the maintenance on the mirrors.
Okay, we have a couple of questions now. First, we are being asked how much rain or weather affect the telescope.
Well, there are some limits about, for example, humidity. I think you cannot operate the telescopes with more than 80% of humidity or something like that. But basically, we have a weather station in Paranal in order to prevent, uh, for example, uh, conditions that are, I don't know, maybe dangerous for the mirrors, such as high humidity, strong wind, rain. Even, well, rain is very unusual, but yeah, sometimes could happen. So when you have basically bad conditions for serving, you need to keep the domes closed, but you will know this in advance. Okay, so probably I know that there is some kind of weather forecast. uh, 36 hours in advance you can know this kind of situation, so you can prepare, and you can of course protect the telescopes, and you need to keep the domes closed. Yeah.
Mhm. And just to complement your answer a little bit, there
Yeah.
is what it calls the dew point, and this is a combination of temperature and also humidity. And the temperature of the dew point is the temperature at which condensations forms in the mirror, and you want to avoid that as much as possible because removing water stains from a mirror is very difficult.
Yeah, exactly. Yes. Correct.
Okay, and we have a here question about you mentioned the images are digitally transformed. That can just be an RGB coded image, can it? For not losing spectral information, should another digital representation method is needed? I can try to answer that. Well,
Yeah, sure.
usually astronomical images are saved in a specific format called FITS. That's .fits, and this format it contains first what we call a header, and the header has information. Uh, what was the date that the images were taken? What was the position in the sky? What are the units in which the amount of light is being recorded? And so on and so on. And in this header, you will eventually also add things like how were this image processed later on in post-process. And you can have many headers, but you have a principal header, and you can also have many extensions containing the data. And the data is kind of like a matrix with numbers, one position for each pixel in the detector, and you just have a number indicating how much light reached that point. And this is all just black and white. We have to create the RGB colored images later in post-processing by combining one essentially black and white image taken into red, one into blue, and one into green. And then we do an RGB color image. But we can also do a combination that is not RGB. We can combine X-ray with observation in a specific hydrogen line and things like that. So yeah, we use a specific format that track information from the telescope, the time that the image was taken, and so on, and also the information read from the detector. And in the case of something that has like a spectrograph, or in the case, for example, the Muse that has a is what we call an integrated field spectrograph, in which for each pixel in the image we have a spectra. What we actually have is that we have many extensions with data, one for each wavelength that we're measuring the data. And that way we can have the spectral information for each pixel. I hope that sort of explains it a little bit.
Okay, thank you. Um, okay, so maybe we can continue. I think we don't have more questions, right?
Yeah, we don't have any more questions so far, so if you have any more doubts, please send them, and we'll try to answer it later on the tour. And for now, we can continue.
Okay, thank you, Hector. So let's continue. So, as I told you before, we are going to visit now the control room. Uh, so we need to move to this location. I will show you the workplace of the astronomers. And this place is basically on the last floor on this building. So we are going to access now. And here we are. So as you can see, we have several separated workstations. This is essentially an office space. Okay, so for example, here we have a workstation for one specific telescope. This workstation is for the Melipal telescope. Okay, so all the operations with Melipal are from here. So you have different terminals for different purposes, some computers, and we have some people working there that they are working specifically on that telescope. Now, in the opposite direction, we have another control, um, let's say another control room for the Jepun telescope. So same situation like before, we have different computers from different purposes, and you have some people working there specifically on the UT4 telescope. Now we are going to visit the other workstations, and you will see the workstation, for example, of AN2, the UT1, and this is the workstation, the last one, for Kuyen. So this kind of workstations are basically, I mean, we don't need a lot of people, okay? So essentially we need something like 2 or 3 people per station. And well, of course, they are working all night. This is a very comfortable environment. It's warm at night, of course, and you have all the necessary tools for doing your observations. So essentially, all the telescopes, instruments, and systems explained before are controlled from here. So during the day, engineers, technicians, and scientists are working to prepare the telescopes for the next observation night. So each night we have a telescope operator and an astronomer per telescope. So for example, in this picture, right now, I am in a workstation, specifically in the workstation for, uh, um, I think this one was for Kuyan. So this person is, for example, the telescope operator, is the person in charge of all the movement of the telescope at night. So it's something like the pilot of the machine. And here we have usually an astronomer. So let's suppose this person is the astronomer. So the ESO astronomer is in charge to direct the scientific observations, and this person will decide the next step. So he's like the co-pilot. Okay. So the observations are performed by experts from ESO for scientists from all the planet. So this is essentially what happens here. As I told you already, this place is not full of people at night. Maybe in all the control room, we have around 10 or 15 people, no more, and they are working all night to supervise the observations. Okay. Okay, so this is essentially what happens here. It's not a super big place. So we are going to return now to the platform, to the telescope platform, because at this point, well, you have a lot more information about the observatory and the people working here. So now I want to invite you to know more about the main scientific milestones made from all ESO observatories. I mean, from La Silla, Paranal, and Chajnantor, because, well, scientific staff from different countries are using the ESO telescopes to study objects near to our home, the solar system, but also others located in the more distant places in our universe. So now we are going to explore a list of the top 10 discoveries from the ESO sites so far.
Observations with ESO telescopes have led to many breakthroughs in astronomy and, over the years, have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history, elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at La Silla was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang Theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam, or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when 2 independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
Okay, so this was the top 10. I hope you enjoyed. But we have just one more thing. We have something like a bonus track. This is somewhat old news, but it's very interesting anyway. Well, a team of astronomers was able to capture the first image of a black hole. So the Event Horizon Telescope, or EHT, its acronym, an array of 8 ground-based telescopes distributed on the planet, working as an international collaboration, was able to achieve the first direct evidence of a supermassive black hole. So the picture will reveal the black hole in the center of Messier 87, a massive galaxy in the galaxy cluster in the Virgo constellation. So this object is located 55 million light years from Earth, and its mass is about 6,500 million times the mass of our Sun. Okay, so we hope you liked the top 10. This was only a fraction of the discoveries, thanks to the ESO telescopes and the scientific stuff behind them. So now we can continue. And from the platform again, we are going to do a very special activity thanks to this virtual tour. We are going to observe the night sky from Paranal. So as you can see, the sky is almost completely dark, with the last traces of light from the twilight. The moon is below the horizon, and the sky is full of stars. So here we can see next to Antu, a little bit up, we can see something very interesting, a very popular constellation. Okay, as you can see, it's just above the Antu telescope. So this one is Orion, the Orion constellation. I will do a close-up to show you Orion. In the mythology, this represents a hunter. Okay, so you can recognize this constellation because we have those 3 stars there, somewhat aligned, representing Orion's belt. And inside of Orion, we can see another interesting object, the Great Orion's Nebula. So this is a star-forming region here, and it's a very bright object because, well, you can look at this object even with your naked eyes, and of course we can observe this with binoculars or even small telescopes, and of course it's very, very impressive. Okay, so now we are going to change the view, and we are going to move to another position in the sky. We will move to the brightest star of the night sky. The brightest star of the sky is called Sirius. It's right here. So Sirius belongs to another constellation, belongs to the Canis Major constellation. And Canis Major represents one of the Orion's hunting dogs. So essentially, the constellation of the Sirius star is connected in the mythology to Orion. Okay, so and by the way, this region in the sky is visible from both hemispheres, from the north and the south hemispheres. Okay? Now, let's go a little bit down, and let's focus to Antu. And you can see that next to Antu, right here, we have another interesting object, right here. So this object is an open cluster, an open star cluster. This is Pleiades, the Pleiades, an open star cluster located in the Taurus constellation. Okay, so usually with your naked eye you can see up to 7 stars. That's why in the mythology you can probably you can find those this object named as the Seven Sisters. Okay. So the majority of those objects, if you look carefully, are visually close to a specific area, very populated with stars. So if you look at this area here, it's very clear that you have a more concentration of stars if you compare with this area or this area. Actually, we are looking at one of the Milky Way arms. This is our galaxy. And our sun, of course, is only one among hundreds of millions of stars. So during the winter in the southern hemisphere, we can see the center of the Milky Way. And the center of the Milky Way is another area full of stars between the Scorpius and Sagittarius constellations. So, and something very interesting, of course, is that you can see all the center of the Milky Way from the southern hemisphere, and you can see all the Milky Way actually from this hemisphere in the winter months. But I mean winter in the southern hemisphere. I mean May or June, July. Okay. So now we are going to move to another sector in the sky, a sector that is dominated by two spots. I mean, two bright spots. So it's right here. So what is this? The spots here are the Magellanic Clouds. So up there we have the large Magellanic Cloud, and down there we have the small Magellanic Cloud. They are not actually clouds, of course. They are galaxies with an irregular shape, both visible to the naked eye in a clear night like this one. This name refers to the records from Ferdinand Magellan during its circumnavigation of the planet in the 16th century. So during this time, the people have no idea actually what a galaxy is. So that's why we keep this name, the Magellanic Clouds. Now, another area next to the Magellanic Clouds is this constellation. This is the smallest constellation in the sky, and it's called the Southern Cross. So the Southern Cross is tilted in this picture. And this is a very easy constellation to find in the sky. It's only visible in the southern hemisphere, and it's a good guide to find the South Celestial Pole. The South Celestial Pole is a projection of the Earth's South Pole. So during the night, these stars appear to revolve around this point. So in order to find this point in the southern hemisphere, because here we don't have any bright star next to the South Celestial Pole, we have to use the Southern Cross constellation. So essentially we have to project the a longer stick of the Southern Cross about 4 times and a half. So if I do this right now, I will project 1, 2, 3, 4 and a half. So more or less like here, we have the South Celestial Pole. So this point, if you look at the horizon, looking toward this direction, you are actually looking at the south cardinal point. So this is a good way to don't get lost if you are in the desert at night. So you can, well, basically get the cardinal points using the stars. Okay, so in this way, I am concluding the visit to Paranal at night. I will come back to the platform because now we have to start to finish this virtual tour, and we have one last stop, and this last stop is the residence. So we have to come back to the platform by day, and I have to rotate the view because we have to come back to the Paranal base camp. So I am going to rotate the view, and I will show you basically the base camp that is located at 2,400 meters above the sea level. The Paranal mountaintop is at 2,600, but base camp is at 2,400. So this is the base camp. As you can see here, it's like a mini city, you see, because we have different facilities here for the workers. But I want to focus on the residence, because the residence is a very special place. It's basically the place where the ESO staff can stay and rest. So we have to access to this place using this ramp. I am going to do that right now. So basically, the residence is the home of all the ESO staff when they are working in this observatory. All the people in Paranal are working by shifts, by shift systems like 8 by 6 or 7 by 7. So as you can see, this place is very beautiful. We have some nature, we have a swimming pool, and we have all the necessary facilities for the people working in this very isolated place. So we have the restaurant over there. We have the lobby there. We have a reception. So the place is very similar to a regular hotel, but this place is only for the staff. Okay, so that's the only difference. The residence has 108 rooms, and it's usually full, but again, it's only for the staff, so it's not for tourists. Okay, so with this panorama of the residence, I am finishing this explanation. So I don't know, Hector, if we have some last questions from our research.
We have a few more greetings. We have Enyo here from Milan. Peradi who says hello from the Ersatz OPSI. We have Merita from Finland. We have Tony Gibson that says very interesting, thanks. We have a question here from Steve. He's asking us about the angular resolution of the interferometry with all the telescopes.
Well, something important to understand is that the baseline you are getting when you are combining the telescopes will depend on the how many telescopes you are combining. If you want to combine the big ones, well, essentially, if you are combining all the big telescopes, you will get a baseline equivalent to the distance between them. That is 140 meters, I think. So depending on this configuration, for example, as far as I know, you get something like 0.4 milliarc seconds, and depending on the different bands that you are using, this resolution can be different. But to give you something like interesting example or analogy, you could distinguish, or you could separate the lights of a car from a distance from the Earth to the Moon. Okay, so or yeah, this is more or less a good example to mention. But as far as I know, and I'm coming back to the question, is about 0.4 or 0.45 milliarc seconds. I don't know, Hector, if you have more accurate detail about that.
Not really, no.
Okay, well, but this is about between 0.4 and 1.5 or something like that, because it depends on the band that you are using, right? It depends on the part of the spectrum.
Yeah, to complement that, there is what the astronomers call the spectral resolution. That is sort of like the angular resolution, but divided by the wavelength, and in that sort of units, you get a value that can go up to like 5,000, which is a very high resolution. But depending on the band, can also be lower for about mid value of 1,000 of something, 2,000 of something.
Yeah, and if you are using the auxiliary telescopes, your baseline will actually be better because in the more when the telescopes are more separated, you can get a baseline of 200 meters. This is the maximum separation of the small one. So you can improve your resolution like 1.4 times better or something like that. So essentially, something important also to mention is that interferometry is very useful to get more details on bright objects. Okay, so this is important because when you are doing interferometry, it's not a real 200-meter mirror. It's not a real 130-meter mirror. It's a simulation using the different telescopes. So you will get more details, and as long as the object is more or less right. Okay? If you really want to observe fainter objects with detail, well, you need a larger mirror. So that's why with the ELT we expect to get even better pictures because you will see the actual fainter objects.
Okay, I don't see any more questions. So for my side, I would like to say goodbye to our audience and remind them that we're doing these virtual tours every Saturday. We are alternating between La Silla and Paranal Observatory and between doing them in English or in Spanish. So keep an eye out for when the next tour is going to be.
Okay, thank you. So we remind you that all these visits, information, and pictures are available on the ESO website. So we invite you to visit our website for more information and of course to stay updated about the next virtual tour, Spanish or English, Paranal or La Silla. Okay, so that's all. So I hope you enjoy this virtual experience. So on behalf of PISO, I want to say thank you very much for your presence. Thank you and goodbye.